Yes. Okay.
Could you revisit some of these things you were trying to say about the previous class to that regarding this torus correlations? That when you do the sum over phi r in this phi r and phi rc,
Yes.
the identification, you were saying there's some spin structure sum and everything. You justified that there's a half into 1 plus PGSO.
Yeah.
And also the sum over
spin structure. Yeah. Sum over we are bound. Yeah.
So effectively, this is like taking GSO even states.
Yes.
In both R and NSA.
Exactly.
But I didn't quite get your justification for half and what you were saying something.
Oh, half is because the projection that involves a half, right? Because suppose you want to suppose P is the GSO projection of GSO parity, right? So if you want to project to even GSO parity states, you have to write half into 1 plus P, right? So that requires that there is if you are using introducing the projection operator, you insert a half, right? And 1 and P corresponds to two different boundary conditions along that circle, right? Because P twists the boundary condition, 1 doesn't do anything.
Yeah, but from the perspective of spin structure sum, it should just come in 1 plus P. Like R plus NS, it's like 1 plus P because there are 4 kind of things you can have. Either you have
no, R plus NS we have, that is in the other cycle, right? There's no half corresponding to that, right? Half comes when you are projecting in a R sector, right? You want to make a GSO projection.
Why do you want to? I thought it's naturally coming because of the spin structure.
No. So I'm explaining why there should be a spin structure sum.
Okay.
Right? That if you want to explain why there is a spin structure sum, right? There is a one sum because you are summing over R and NS. The other sum comes from the projection operator because that's half into identity plus P. Right? A projection operator is half into identity plus P, right? P is the GSO parity.
Okay. I have this perspective that, like for instance, any genus, the handle is like adding a loop, quantum
yes.
kind of way, and you let everything propagate in the loop.
Everything which is GSO even.
Yeah, but I mean that should be automatic. No? For instance, you are not restricting to any cohomology or anything. You're letting off-shell states also.
Exactly.
Propagate.
Yeah.
So GSO even, I thought.
But this is not off-shellness. GSO even or odd, right, is different.
Yeah, I agree.
Because this is a projection, because this is basically from the beginning itself, you have said that your configuration space is not xi psi tilde, but xi psi tilde modded out by this identification of xi psi tilde with x minus psi tilde, right?
Yeah.
Okay? So the configuration space itself is different. You have to put that information somewhere, right? Otherwise, you might as well have worked in a theory where you have just xi psi tilde without any identification, right? In which case there will be no GSO projection, right? And there will be no Ramond and Nebu-Swartz separate sectors. So this fact that you are identifying xi psi tilde with x minus psi tilde in the configuration space has to go in somewhere, right? And that's what tells us that you have to sum over spin structures.
This fact that xi are identified to minus of themselves, and basically it's the fact that we need GSO even objects, but you're saying that this should be there in the off-shell states also, right?
Exactly. Yeah. That this should be there in off-shell states also. Well, originally, you need modular invariance. That comes. Yeah. So the original motivation was that only, right? That if you want to define a consistent string theory, right, you couldn't do it just by one boundary condition. Okay. Because that will be just one sector. The point, of course, this came after a while, right? That's why these are different names, right? One is NS sector, one is R sector, right? Nebu and Swartz worked with their boundary condition. Ramond worked with the other boundary condition, and later on it was realized that you have to somehow combine them to get a consistent string theory, right? And on top of that, you have to this GSO is another set of people, right? Geodesics are colleagues. So all these things came piecemeal, right? But eventually, one now understands that to define a consistent string theory, all of these have to come together.
Right? We only kind of measure the external depths or external states in any
Hello.
Just me, you're muted. Hello?
Yeah, can you tell him that he is muted?
And then there is a pure spinner, right, which is more complicated, but it works at least up to 4 loops, it can give the result. But it's the wall sheet theory is not a free theory. Wall sheet theory is complicated.
And it does not use any GSO projection.
It doesn't use any GSO projection.
Still guarantees the modular invariance.
Yeah, but the wall sheet degrees of freedom are not psi mules. Right? There are other various other fields which are spinors of space-time.
So space-time or the?
Of space-time.
target?
Spinors of space-time. Target space, yeah.
DCFT.
Yeah, but what quantum number the fields carry, right? In terms of SO9, 1. SO9, 1 is a global symmetry of the theory, right? And you can choose what fields you want to add under that global symmetry. Right? And this pure spinner uses fields which are in the spinor representation of that global symmetry. Right? Both green swartz and pure spinor. Yeah, typically what happens in a pure spinor formulation, in different dimensions, you have to use different formalisms.
DSO way of wind has no, I mean, you can take whatever target.
Yeah, yeah,
Just a 2D CFT.
exactly. Because as long as you have X mu's, you have psi mu's, right? So there is a confusion about the dimension of space-time doesn't enter in a non-trivial way till you discover that D has to be something to for the conformal anomaly cancellation, right? But pure spinor, for example, yeah, from the beginning itself, you have to make a choice of which space-time dimension you are working.
If I don't want modular invariance,
Yes.
like at tree level only, so do I have a motivation to take GSO projection there?
No, no. At tree level, if you just want the spectrum, for example, right? You can work with NS sectored states without GSO projection.
Also pointing out that it's really the torus that makes you include all.
Yeah,
factors and
exactly. Yeah.
also the
Yeah.
spinor.
It's like if you have an Ising model, right? Ising model has 3 primary fields. Right? 2-dimensional Ising model has 3 primary fields, but one of them, there is a Z2 symmetry under which one is odd. Right? So you could decide that, okay, you will only include the Z2 even states, right? All correlation functions will be perfectly fine because no, the Z2 odd states will never appear in the intermediate channel, right? So if you try to use conformal bootstrap on the plane, right, you will not find any error, right? It will be consistent with every crossing symmetry and everything else. But once you go to loops, the torus, right, then you find that you lose modular invariance unless you also include the Z2 odd state. Is this clear? Any other question?
You said something about that we will have to do the 2G terms at genus G.
2 to the 2G terms, yeah. No, 2 to the 2 to the G terms, I think.
2 to the G term.
Yes.
Because torus has 4. RNS, GSO, even.
Oh, yeah, yeah, okay, yeah. But the factor, 1 over something, that is 2 to the G. Yeah, 1 over 2 to the G. Yeah, you'll have 2 to the 2G terms, indeed.
2 to the 2G term.
Yeah, yes.
For genus 1, I'll have 4.
4, yes.
Like when I calculate the partition one.
Yeah, yeah.
Because every tube actually gives 4, right? You're saying in this direction and this direction.
Exactly. that
It's
side.
like one plus some, like I have two terms, time two terms. That's
Exactly.
How you.
Yeah,
say it.
yeah.
And for, okay.
Right, 1 plus P and both in NS sector and remote sector. Is it okay? Other questions? Okay, so today we are going to discuss amplitudes in superstring theory, right? Because you already have our vertex operators. Okay? So with these vertex operators, you can now try to build amplitudes. Okay? So I'll begin by describing what happens in the case of bosonic string theory, right? That we had discussed it earlier, but I'll just remind you. Okay, what the expression for the amplitude is for bosonic string theory. I think the chalks have disappeared. There is chalk there. I mean, there are a lot of maybe colored chalk, but no white chalk. I think they were too small. Okay, thanks. Thanks. The amplitude was given by integral over the moduli space. But these are the vertex operators, all unintegrated vertex operators. So these are barest invariant objects. Okay. And omega GNP is a P form. P form on MGN. Okay. And this was given by -1 over 2 pi I. Okay, I'll explain what does P's were. So definition of P. Okay. So there are many ways of defining it, but the way we defined it is that we regard the Riemann surface as collection of disks, which will denote by dA. Okay. And this is one around each puncture. And spheres with 3 holes. So one particular example is the genus 2 surface with 2 punctures. Okay, so suppose you have a disk like this, a Riemann surface like this. So the way we split is
Hello. Uh, you are muted.
Yeah,
You are muted again. Can you hear me?
What happened? Somebody is asking. No.
yeah, hello, Ashok. You are muted. Now it's fine.
Okay. Okay. So this is a picture we had drawn for the bosonic string theory. Okay. And the idea is that we introduce the moduli UI were parameters that label transition functions along across circles. So we introduce coordinates on each, right? So the coordinates we call WA on TA and ZI on SI. Okay. And the transition functions took the form which it is. No, that's inside. There's no space there, right? Yeah. So this is a puncture. I've drawn disc around each. So these are the two discs, right? So this object is a sphere with three holes, right? If you imagine, right? It's like a three-hole spheres, right? So this is this. So let me write this. So this is the first three-hole sphere S1. This is S2, S3, and S4. Right? There are four three-hole spheres here. Right? So on each of those we introduce some coordinates. So there are four ZIs and two Ws. Okay. And then across each circle you have to specify transition function across CS, which we wrote as sigma S equal to Fs. Sorry, I think the way I wrote it is tau S is Fs of sigma S, and U is just some parameters that enter these transition functions. Okay. And sigma S was left of CS, tau S was the right of CS. Okay, you have to just choose some orientation of CS and take one on the left, one on the right, right? So they get related by these transition functions. So tau S could be either Zi or WA, depending on whether the space on the left, on the right is a disk or a sphere. Right? Similarly, sigma S could be a Z or a W, right? Depending on whether it's that side left of CS is a disk or a sphere. Okay. And then the BI was given in terms of these. BI was integral, first of all, sum over S, integral over CS. Yes? Yeah, these are the same moduli specified, right? Because either the moduli space is labeled by these transition functions, right? If you want to go move to a different point in the moduli space, what we'll do is that you will change these parameters U, which will in turn change the transition functions. And that typically takes you to a different point in the moduli space.
The upper limit on I we have not set, right? I mean, the range of I.
Yeah, range of I is 1 to 6g minus 6 plus 2n. Right? Now, of course, inside the transition functions, you can have many more parameters. Right? But if it is anything more than 6g minus 6 plus 2n, those are redundant. Right? Which means that by changing, making a redefinition of z's and w's, you can get rid of those parameters.
Here it should be 10 in the single.
For here, it's g is 2, so 12 minus 6, that is 6, yeah, it will be 10. No, you will not see this. This is a topological result, right? The number of parameters that you can introduce inside is you can use 100, you can use million, right? Because they are functions, right? So a function can be labeled by a million parameters, right? You just take sigma s plus sigma s square plus sigma s cube up to sigma s to the million, right? Each coefficient is a parameter. But the claim is that all those parameters can be shown to be redundant, right? That means they can be removed by field redefinition, except by redefinition of coordinates, except the 6g minus 6 plus 2n.
Oh, these are, we should use some different index. That I have not to do with this.
No, yeah. So let me call this Z alpha maybe.
I mean, there is a limit on the modular parameters ui that this can take this 60 minus 6 plus minus 6 plus 2n value.
Yeah.
There has to be a reason for it, right? Why this number?
Yeah, so this comes from this topological analysis. Yeah, there is something called Riemann-Roch theorem which actually counts how many moduli you have. Okay? That is certainly not visible from this. Okay? That is a separate knowledge that the moduli space, like the torus, for example, right? I mean, you can do this for torus. Okay? Torus has 2 moduli. I mean, proving that, I mean, if you can also think of torus as spheres connected, right? But proving that it has exactly 2 moduli, right, requires effort, right? It will not follow because the transition functions, again, you can take infinite parameter transition functions, right? Even just across one circle, you can have infinite parameter transition functions.
I think you have to somehow argue that it can't go negative of that value. I mean,
it can't go.
For instance, if I take the genus 0 surface, but the number of insertions n to be less than 3, then
yeah, yeah, because then there is SL2R, SL2C, part of SL2C is unbroken, right?
So that is not
Yeah, exactly, right? So on the torus and on the sphere, this issue is there, right? Because torus has translation, right? So torus without puncture is problematic. Torus with 1 puncture is okay, right? That has no modulus. Sorry, that has 2 moduli, okay? Because you have fixed the translation invariance.
And can we start with this just pair and do this insert this completeness relation every time to get this for every genus this value this 60 minus or no?
You can. There is a standard construction by which you can do that, right? But every time you glue, right, there are 2 parameters, 1 complex parameter that comes, which is that you want to have Z1 and Z2, right? Earlier we had taken Z1, Z2 to be product to be 1, right? If you want to allow Z1, Z2 equal to Q, right, which basically means that you can rescale one of the coordinates, right? Or Z1 and Z2 by Q to the half and then glue them, then join them, right? So that parameter, if you count, right, then you can get this number.
Plus 60.
Exactly. But the point is that you have to prove that you cannot get anything more, right? Or that all of these that you are getting are independent, right? So that requires knowing the theorem that there are these many parameters. Okay. And basically what happens is that almost any function that you choose labeled by 6g minus 6 plus 2n parameters would be fine, right? In fact, you can include all those parameters in just one transition function. Say that all other transition functions are fixed. You have chosen them to be fixed functions once and for all, right? And across this disk, you take a transition function that has 6g minus 6 plus 2n parameters. No dependence on u, right? Which means they're fixed functions. You choose whatever, right? Sin x, cos x, I mean, you choose some function, fix them, right? And you introduce a parameter u only across 1. Right? Even that is fine, right? Unless you are unlucky that you end up into a parameterization which can be removed by change of coordinates. Right? Any transition function that you choose is fine.
I'm looking, so different views should just correspond to different points in the modulus. That is the only thing.
Exactly. But sometimes, I mean, what I'm saying, if you choose it at random, this parameterization, then you will get the correct number. Then you will ensure that by change of coordinates, you cannot relate them. Right? Because relating two transition functions by change of coordinates, right, is highly unlikely, right? Because if you choose the transition functions out of your head. So if you choose at random, right, say 1 fs, okay, parameterized by 6g minus 6 plus 2n parameters. Those 6g minus 6 plus 2n parameters will be able to label the moduli space. Is this clear?
Whatever kind of, invariant we have. First of all, we have the choice that we can take any sort of parameters ui as long as they are restricted by this number. Right?
Yeah.
We can take that. Right? That's the choice of parameter.
Exactly.
And now the choice there's one more choice of the transition function, which is in a sense the function of these parameters.
No, wait. These are the same things. So I didn't understand. What?
And the transition function is different, right?
Fs.
Yeah, that is fs or tau as well.
Yes.
There also we have a choice, right?
That choice is inside this u. When I put the u, right? When I put the u, suppose you take a one parameter family of transition functions. I'll call that parameter as u, right? So whatever choice you have, right, that is what I'm calling u. Right? You can choose sin x or cos x. So these are two different transition functions. But you can take sine of x plus alpha, right? And take alpha as a parameter. Then by varying alpha, you may get sin x for one value of alpha, cos x for another value of alpha, right? Or if you want to take two different functions, you just interpolate between those two,
So
right?
all these choices are just coming to the reparameterization. In a sense.
Yeah, except for the ones which correspond to moduli. You're not reparameterization u, reparameterization sigma s and tau s, right? That most of these can be removed because you can take infinite number of parameters, right? As I said, right? I take a million functions, take a linear combination of those million functions. So there are a million parameters in that combination. Right? But this theorem tells us that most of those can be removed by change of coordinates, right? Except this 6g minus 6 plus 2n. That's not easy to see, right? It requires some effort to actually establish that this is the correct dimension.
In conformal gauge, I mean, I can see, right? I mean, I can at least find that these are in one-to-one correspondence with the holomorphic quadratic differentials that can be.
Yes, that's right, yeah.
And that will be, I guess, that mu, and then I will need to see corresponding to the residual gauge transformation. There will be something. And
Exactly.
subtraction of that is this number.
Yeah. So residual gauge transformation is exactly change of coordinates of the z's and w's, right? Because those don't change the if the metric is some function times dz mod square, change of coordinate of w or z, right, keeps it in that form, right?
Yeah.
Is this clear? So here, basically, what one is doing is that instead of trying to label the space in terms of the metric, right, which is a more complicated object, this is what is called complex structure. That you have different choice of these transition functions correspond to using different complex coordinates on the surface. Okay. If you are interested in the real surface, okay, if you don't worry about the complex structure, then all Riemann surfaces of a given genus are diffeomorphic to each other. Right? You can just change coordinate to make any Riemann surface into any other Riemann surface. Okay? The only reason that they are not all the same is because the complex coordinates that will be different, right? that you cannot make a complex coordinate transformation or analytic coordinate transformation to take one Riemann surface to another Riemann surface. Okay, and the abstraction to doing that is this 6g minus 6 plus 2n.
These are not the Beltrami difference.
These will be the, yeah, they can be made into one-to-one correspondence with the Beltrami differentials.
Oh.
Okay, these ones. I mean, these are some special case of Beltrami differentials where there's a jump, right? It's like a delta function localized on the circles. Beltrami differentials is more complicated object. You write it as integral d to z instead of a contour integral.
Okay.
Right? Here, the analog of that is that there are a delta function localized on these contours. Right? So you have a contour integral.
But I would think these are less in number than the Beltrami.
No, the same. Because 6g minus 6 plus 2n, right?
Okay. But I used to think that was mu, like larger, and then I subtract. Or probably, I guess, yeah.
Okay, it depends on what you mean by Beltrami differential. Yeah, normally I'm thinking of Beltrami differential as after you have done all the modding, all the quotient, right? What you can change by coordinate transformation.
All the super part of heterotic and all that are already gone in.
No, this is only bosonic. This, I just reviewed what the amplitude that we gave for bosonic string theory. No, it is almost what you are supposed to do. That's why I've written it, right? Otherwise, I haven't spent so much time writing it. Okay? Because once we have given this, right, now I'll tell you what is the extra for superstrings. Okay, but all this you have to do for superstrings also, for superstring amplitudes. Is this clear? So for superstrings amplitudes, heterotic string, right? Because I'm taking only one sector. Type 2 will be just doubling of this. Heterotic string amplitudes. With m ns and n r states. Okay. First of all, we label the moduli space as MGMN. Okay. This is somewhat superficial because I could have written it as MGM plus N, right? The same moduli space. Okay, except that this MGMN, that when I write integral over MGMN, okay, it will be understood that this also includes integral over sum over spin structures. Right? So when I write integral over MGMN, right, this means that you are also summing over all spin structures. Okay, otherwise it's the same space. Okay, there is a difference between the bosonic and superstrings. Okay. So the difference is that first you have to insert product alpha equal to 1 to 2g minus 2 plus m plus n by 2, the picture change of pattern. So these are some arbitrary positions, points on Riemann surface. No, the alpha I'm going to change to something else. So let's try to change it to something else. Even though there's no space-time index involved, I'll put mu. Okay, don't worry about the x mu's, etc. So the number of these is this much, right? Why? Because we know that the picture number has to be 2g minus 2 on a genus G Riemann surface, and the ns sector carries -1 each, so that has to be compensated by putting m, and r sector carries -½ each, so it has to be compensated by putting n by 2. Okay, and these are of course in integer because the number of Raman sector states is always integer. Pardon? N is already even. Yeah.
So it's trivially zero.
Yeah, that is trivially zero. Right? Odd number of fermions you cannot have in an amplitude. So this is the first difference, right? So in this amplitude, here you have to insert that product. Yes, this is equivalent to doing supermoduli integral. Basically, this is the reason that this chi of y alphas come is because the integration over the fermionic moduli bring down this chi of y alpha.
Brings down, I mean, that those will be fermionic, so there will be just one term in the expanded.
Exactly. Exactly.
One set of terms.
One set of terms, yeah. So each supermoduli brings down one chi. Okay, and there are these many supermoduli that you have to use. The second is that we have to add to Bi there is one more, 1 over, let me write it beta.
One of the conditions is to not.
No, I didn't say that. If you that if it didn't depend on you, then you didn't have to add this term. Because earlier I had said the amplitude, when I wrote the amplitude, I said you have to insert the picture changing operators. Right? And you stop there if the y's don't depend on you.
To get a finite answer for a correlation function on a sigma g from n, you said the full picture number should be 2g minus t.
Yes.
And if you have m and n, you need to put as many guys to balance out the picture number to get 2g minus t.
Exactly.
And one of the conditions you said something like y alpha should be taken independent of the moduli.
So if the y alphas are independent of the moduli, then just inserting picture changing operators is good enough. Right?
We can do that here.
For the amplitude.
For the amplitude, yeah.
Correlation function is fine.
No, correlation function is okay because this object, right, carries total picture number 0, just like BI's.
Yeah, I'm just saying 1 over, right?
Yes, 1 over chi. So you should have objected earlier, right? Yeah.
See that?
Yeah, exactly. It's 1 over chi. So del xi has picture number 1, chi has picture number 1. So they cancel, right? So the reason that this makes sense, this is the reason that it makes sense, yeah, that is the following. This is formal. Okay. Then ultimately you are going to put it in that, right? And expand out. Okay, in the expression for BI, you have the product of the BI, right? So when you expand this out, right, del xi y beta, right, cannot come more than once, right? For a given beta, right? Because the product is 0. Del xi y beta at the same point is 0. Xi is fermionic, if you remember, right? Okay. So when you expand out B, right, you will pick up del xi y beta from once in a while, right? From the some of the BIs. But never the same beta twice. Okay. Which means that in this expansion, the 1 over chi of y beta, okay, will basically appear at most once with a particular beta, right? So okay, 1 over chi, see, if you had one factor of 1 over chi y beta, right? Then there is a confusion because there is this factor is there, right? It just says that you just remove a chi y beta, or cancel off, yeah. You just remove chi of y beta, right? That's what this means. The problem would come if if there's a 1 over chi y beta square, right? No, the same chi y beta, if it appears twice, then two different b's, exactly, because each b has all the chi, all the betas, right? Exactly, all the 1 over chi's are there in each. Exactly. Exactly. Yeah,
But the del xi, y by del xi, y
will vanish, right? So that's why in this expansion, right? So this is a formal result, right? There is a probably different way of writing it, right? But basically 1 over chi is a formal thing. It just says that you have to remove from this product an appropriate factor of chi y beta.
How did you figure this out? Like, there's some logic to it.
Yeah, so there is a logic to it. Basically, the logic comes again. One of the logic is supermodular integral, but I'll describe a different logic. That's basically using BRST invariance.
Yeah, but then it looks like that the fact that there is a del zeta is not that important. You only need some Fermi or Grassmann odd number there.
Yeah, no, you need precise del zeta, del psi. No, nothing. Yeah. So if you want to get the correct superstring amplitude, you need this. Yeah, just for making it 0, you don't need this, right? Then you might not even have added this, right? This is the one which is needed for getting the correct superstring amplitude.
Side of things being non-vanishing only when xi and eta, number of xi's are equal to number of eta in the small element space.
Yes, that is true. That will happen. Otherwise, the result will vanish.
Okay, B's will come with certain number of etas.
See, this one doesn't do anything to other picture number, host number, anything. All conservation laws are satisfied by this.
You should think of 1 over chi as contribute. Okay, this thing has a what xi.
Yeah, this thing together, see, there are xi's all over, right? From inside these, there are a lot of xi's and a lot of etas. Etas also, right? Chi has both xi's and etas. Because it starts from C del xi and ends up with this del eta e to the minus 2 phi b, right?
There's some precise line.
It has some xi's and some etas. And then there are also terms without xi's or etas.
Yeah, I'm just saying if the B of this B,
Hmm.
does it have a precise xi minus eta contribution?
Yes, it does.
What?
0, yes.
So you should think of 1 over chi as
1 over chi is whatever it is, right? It will just cancel one of the chi's. So you lose that, whatever that chi you are supplying. Yeah, okay, this doesn't have, maybe I should say this, this doesn't have a fixed xi minus eta, it has a fixed picture number, right? Xi minus eta, whether it agrees, right? That depends on ultimately, because see, none of the, this also doesn't have a fixed xi and eta quantum number, right? Each chi doesn't have. Each chi has its del xi in the beginning and there is eta in the end, right? After you take the product, right, you never have to calculate 1 over chi, right? 1 over chi basically cancels 1 over chi. Ultimately, you have the product of the chi's and del xi's. Okay? From that product, you have to get a non-zero answer, you have to make sure that you have equal number of etas and xi's. Only those terms will contribute, the others will not contribute. Right? So there are lots of terms from here which will not contribute. Right? Imagine that you pick the eta from every chi, right? Whatever is left over.
one from each chi.
Yeah, one from each chi, right? That will not contribute typically, right? Because you have too many etas compared to xi's.
Typical term. Yeah, if you pick the xi term from the
Yeah, if you put the xi term, if you need pick appropriate xi terms, right? Then it may contribute. Okay, let me give the other example. Suppose you put the xi from each chi, right? Then it is definitely not going to contribute, right? Yeah, there is no eta anywhere, right? So a given term in a game, you have to make sure that you have equal number of xi's and etas. Only those correlation functions will be non-zero.
The B's don't come with any xi.
The V's. It depends on what representative you have chosen. If you have chosen the representative where these are just CC bar, Yeah, then it doesn't contain any xi origin. Right, but you can choose to take another representative, right, where you have xi's and etas. Those could compensate. If you choose another representative which has a lot of etas, right, then those could contribute. Exactly, exactly. So this final result shouldn't depend on what element of the cohomology you have chosen, right? That's the reason why this formula has been written in the first place. Right? I'll try to show later why this guarantees that. That if you take another representative of the cohomology, you should get the same answer, right? So that's the logic I'll follow to argue why this choice, right? Not something else. But as I said, if you can, in principle, start with supermoduli space integral and arrive at the same result. Is this clear?
Hi.
Yes.
Yeah,
Go
so
ahead.
in this second part of this modification, you have told that summation over beta y beta. Are these y beta same point where you have inserted the picture changing
Yes,
changing?
same sum. Yeah, same point.
Okay.
Why are
And
exactly the same point?
okay. And another thing is, why does y beta depends on the moduli, this differential that you have written, del yb over del y
Generally, it
del.
could. In general, because y's are chosen arbitrarily, right? And you
Yeah.
could choose different y's as you move in the moduli space.
Okay.
Right? You can keep them fixed, but the more general situation is that when you move in the moduli space, y's could change.
Okay. Okay.
Right? Imagine that if you take a sphere 4-point function, right? Okay, in
Yeah.
a sphere 4-point function, you need to insert, suppose you take the NS sector states, right? So 4-point function will have what? My picture number -4, right? You need two picture changing operators. And it could happen that you keep 3 points fixed, 1 point you are moving, right?
Yeah.
As you move 1 point, you may want to move the picture changing operators, right? In fact, it's necessary because you don't want the point to come and hit the picture changing operator, right? Because that may induce additional singularities. So you may want to have moved the picture changing operators to avoid collision with that point.
Okay. Okay.
So in general, you have to let them vary.
Thanks.
Okay. Any other question? Okay. The second point is that when I write del y beta del ui, right, you have to say in which coordinate system you are specifying y. Right? Otherwise, we can just redefine our coordinate system so that the picture changing operator doesn't move. Okay. So the coordinate system that you have to use, okay, is the coordinate system is where y has been inserted, right? If it is inserted on the disk, then you have to use the w coordinate, right? Then what I mean by y alpha is there is y measured in w coordinate. Okay. If I have put it on a sphere, then that y will correspond to y measured in the z coordinate.
Extra puncture.
There you can think of them as extra punctures. No, we don't think of it extra punctures in the sense that we don't exclude disks around those. No, no. You could probably, but it's not necessary, right? We just think of them as extra points on some of these S's or D's. Exactly.
Then these, sorry.
And then the y's have to be measured in the coordinate system for that S or T, right? Because if you have used put it on a disk, right? Suppose if the y is on a D1, right? Then I have to use the W1 coordinate system. So what we mean by y alpha is the y alpha measured in W1 coordinate system.
I could just put everything in D.
You could, yeah. Okay. You could put everything in D, and then if you say that you will keep y fixed, locally you can do that, right? Locally when you move in the moduli space, suppose you say that you put everything in D1 and you keep those coordinates fixed as you are changing your transition function. Okay. Then all these terms will be 0.
And then that freedom of choosing y, whether it's D or S, that does not matter in the end, right? Because
That will not matter in the end.
because you're saying according to that you have to choose coordinates accordingly.
Exactly.
Omega or
Yeah. No, you can ask. I mean, it looks like there is a violation of continuity because suppose you take y to be close to the boundary, right? and you take it to the other side. Okay? Then it looks like that you cross the boundary and then the coordinate system that you are using has changed. So whether del y alpha del ui is 0 or not can jump by just going across that boundary, right? Okay? And indeed it jumps so that this del y alpha del ui is 0 or not. Okay? But there is something else which jumps, and that's that this contour. Right? You are passing the location of the picture changing operator to that contour, right? Okay? And then there is a residue that is picked up. That exactly compensates that thing that we'll get from there. Okay, if y alpha is independent of w, you say w1, and if it does depend on z1, right, as we just cross this, okay, that extra contribution that comes from bi, okay, is exactly compensated by the fact that in the process of moving it from one side to the other, this contour integral also changes.
This is one of the reasons why this extra term has this factor. I mean,
Exactly. I mean, you can say this is a, yeah, this is a consistency check, that it better have that factor, right? Because the final result shouldn't depend on whether if we move it a little bit. Pardon?
Why will this jump?
Because B has a non-zero OP with picture changing operator. When you are moving y alpha, chi is changing, no?
But this is just the ghost.
Yeah, but the ghost, when you are moving y alpha from inside to outside, right, outside the contour, this integral is going to jump because B has a non-zero OP with chi. Remember, B has a C del xi, chi has a C del xi, and the first term in chi is C del xi, right? So the BCOP will give a term proportional to del xi.
I think in the expansion, that sort of term will have a jump.
Yeah, that in one case, there are two things. In one case, you have this, and the picture changing operator is inside, right? And imagine that this is inside and this is not changing as a function of w. Okay. In the other case, it is outside. Once it's outside, you have to use the Z1 coordinate system. Right? And the Z1 coordinate system may change as a function of w. I mean, in the Z1 coordinate system, y alpha may change with moduli, right? Because the relation between Z and W is controlled by these Fs, right? Okay, so if the W coordinate system it is not moving, then the Z coordinate system in general it will move, right? Because of this Fs.
I think this contour integral cares, since B has a non-trivial OP with these guys and all, it may care about whether there is chi insertion.
Exactly. Exactly. This contour integral will care about whether the chi insertion is here or here, right? And you can calculate how much it cares, right? That's determined by the OP, right? And that OP is exactly what will compensate that extra term that you get.
The OP will have some del xi.
Del xi, yeah, because CZ del xi is the first term, right? That's the one which will have a non-zero OP with B, right? So BC OP will just give you 1, right, from the residue, and so you are left with this del xi.
Chi has a C del xi term.
Chi has a C del xi term. No, 1 over chi you forget. 1 over chi is basically saying that there are two. You either have a chi or you have a del xi. Right? Exactly. You can reduce. I mean, it's just a convenient way of writing it. Right? So 1 over chi doesn't mean that you have a 1 over chi. Right? It basically means that you remove the chi. Right? That if you have a del xi, then you remove the chi. So yeah. So every term in the product either has a chi of y alpha or a del xi of y alpha. Right? Exactly.
Is overall normalization fixed? I mean, here or
Overall normalization can be fixed by factorization. Right?
factor it?
Yeah, because again, you can start from a sphere and factorize, right? That will tell you how to fix overall normalization. That the same way we build the torus amplitude. The overall normalization is fixed. Okay, once you fix the normalization that way, right? I mean, as I said, there's no ambiguity because you can start from a sphere and start putting these handles to get torus, right? So there's no ambiguity in defining torus amplitude. In the definition of omega, there is this minus 1 over 2 pi I to this. This normalization will be the same for superstrings. You don't change this. There is no coupling constant will come, that can be put at the end, right? That we can put a GS to the 2n, 2g minus 2 plus m plus n. This m plus n depend on whether you absorb the GS in the definition of the fields or not, right? How you have normalized the fields. We say Young-Mills, right? If you write it as 1 over GS square as the overall thing, then you don't include any coupling in the interactions, right? On the other hand, you can just scale the fields, right? So that you have GS absorbed in the fields, then you have GS to the total number of external states.
So this formula is just the same thing with this redefinition of B
Yeah,
and with some pi's.
exactly. With this redefinition of B and then the fact that you have to insert the chi's. Okay, and with the understanding that's when you write integral over mgmn, right? It should be sum of it also includes sum over spin structures. And this 1 over 2 to the g factor. Right? All that is included in this definition.
That's in the definition of this correlation.
Integral moduli.
No, in the correlation function, when you say sum over spin structure, right? Yeah, that is in the definition of the correlation function or the integration of the moduli. I'm thinking in terms of the integration of the moduli means sum over spin structure. You can say, okay, correlation function involves sum over spin structure, right? Already, or you can say correlation function is for a fixed spin structure, and then you have to sum over spin structure, right? That's formally in the integration over moduli. I mean, it makes sense to include it there because at least if you have one Ramon sector state, right? I mean, if you have only NS sector state, then it doesn't work. Suppose you have one Ramon sector state. Okay, one means you have to have two. Okay? Then by changing the position of the Ramon sector state, right, you can change the spin structure. I don't know if it is clear. Imagine that you have a torus. Yeah, I can erase this. Imagine that you have a torus amplitude. Some vortex operators here and there, and you have one Ramon sector states, right? Now, let's imagine what will that you take this position of this, you are supposed to integrate over this, right? So let's suppose that you integrate over this line. Okay, you go around, you have to integrate over the full torus, right? Of which you can fix the position on the A cycle and go around. Okay. By the time you have come back here, okay, the result doesn't come back to the original value. Because the boundary condition along this, right? If it was periodic before, it gets turned to anti-periodic. Ramon sector state creates a branch cut, if you remember, right? For the fields. So suppose psi was periodic along this cycle, right? No, but the local OP, right, creates a branch cut. No, local is local. That doesn't matter, plane or. No.
When we take psi,
Exactly. Yeah, when you take psi with SOP, right? Then, yeah. So if you take psi to be once around the vortex operator, you become a minus sign. Okay. So now what I'm saying is that imagine that earlier, before you have taken this, earlier, suppose along this, psi was periodic. Okay. Now you take this and go round. In that process, you have cut this psi, this contour once, right? So now when psi goes around this cycle, it will pick up an extra minus sign. Is that clear? So psi will become anti-periodic.
That is maybe short.
Pardon?
I think antiperiodic is maybe short.
Yeah, but on the torus, you talk in terms of spin structure, right? So what will happen is that the psi, as it goes on that, as you take the Raman sector state and go once around the torus, right, the psi will pick up an extra minus sign. Okay, so this means that if you want to sum over spin structure, suppose you have a Raman sector state. If you want to sum over spin structure, right, all you have to do is to say that the location of the Raman sector vortex operator, instead of integrating from 0 to 1 and tau, instead of taking one parallelogram, right, the torus is described by parallelogram, right? 1 tau, right? Okay. You integrate over this. You integrate over this region. Okay. That will automatically sum over spin structure.
So you're saying you can
That instead of summing over spin structure, I'm saying that take a position of a Raman sector vortex operator, one of them, not all of them. That will be double count. Take one of the Raman sector vortex operator and integrate instead of a fundamental on just the fundamental domain, right? One parallelogram. Okay. You double it on both sides.
It's negative,
what
because
integral are you talking?
Pardon?
Which integral?
The integral over the location of the vortex operator. On a torus, you are supposed to integrate over the location of the vortex operator. That's part of the modular integral.
That's this keyhole.
No, that's tau. That's tau, right? This is z. Z, every z has to be integrated, right? Except one. One will be fixed on the torus.
This is the one point one. What are you computing right now? I don't understand.
Multi-point function. There are all these vortex operators sitting here, right?
So there's some endpoint.
N-point function. So there are 2n-1 integral, real integral, right? 2 times n-1. Because 1 point you can fix on the torus, right? 2 times n-1 coordinates you have to integrate over. Besides that keyhole region, right? That's the tau integral. Besides that, you have to integrate over 2 times n-1 locations, right? Of the contours. I'm saying take one of those, which is Raman, which represents the location of a Raman sector vortex operator, and integrate instead of over one modular, one domain, right? Which is this parallelogram. Okay. Integrate over 4 copies of this. One extended in this direction, the other one extended in this direction.
if you have, let's say, n insertions.
Yes.
Out of n insertion, only one insertion is coming from the one sector. We can fix
Not
it.
one, but two. At most two. At most two will be needed, right? But only one you have to integrate over the yeah,
Double of.
double of the torus.
Isn't it automatically takes care of this half into 1 plus PG?
No, half we have to include. Half, there is no, see, what about 2 to the g, right? You have to put, because the fact that it's a projection, the integrals don't know, right?
I meant that it automatically takes over the fact that you have summed over.
Spin structure or periodic and anti-periodic boundary conditions. So if you take one of the Raman vortex operator and integrate over double torus, it will automatically take into account the fact that you are summing over both periodic and anti-periodic boundary condition on the fermions.
Can you write this a bit more explicitly? So you have a d tau integral.
You have in d2 tau integral, right? Yeah, d2 z1 to d2 z n minus 1, right? Or m plus n minus 1. Okay, these are the, if they're m plus n, if that, these are the moduli space integral. Exactly.
You're saying the correlation function.
Yeah, so this is, and then you have the integral correlation function, right? So these integrals normally you take from over this parallelogram,
Over the torus.
over the torus, right? I'm saying that take one of those integrals and do it over the double torus. Okay, you extend the torus in this direction and that direction and do this integral. Okay. That will automatically sum over spin structure.
Instead of having that correlation with 1 plus P applied to and sum over NS and R,
Yes.
now you only have NS plus R sum. And
No, nothing. No NS plus R sum. This already counts down. See, you had 4 terms you said, right? Those 4 terms are these 4.
Coordinator doesn't know, right? Correlator is just insertions and you just.
Yeah,
apply it.
except the correlator knows that it's not in the, for the Ramon sector vertex of water, there is periodicity is actually double.
Okay.
If you take tau to tau plus 1, right, it doesn't come back to the original value.
Correlator, like if at Z1 I have a Ramond.
Exactly.
Insertion, the correlator will have a Z to the half integer power.
Exactly.
That's the reason.
That's right.
that Then we have to.
Yeah.
Double.
Exactly, right? So the period that you will get, right, it's actually double. Okay. Or you don't worry about periodicity. Take the integral from 0 to 1 and 0 to tau, that parallelogram, and then you have to sum over all. Right?
Sum over
All 4 sectors.
all.
Right? For a torus, there are 4 sectors. Right? Periodic and anti-periodic along the A cycle and periodic anti-periodic along the B cycle. You have to sum over those 4 sectors, and that will give this same result.
But this is somehow telling me that I cannot fix the Ramond insertion position. Like I have to fix one, right? That
Yeah.
has to be always NS or.
No, no, you can fix Ramon.
I can fix Ramond.
Yeah, you can fix
Then
Ramon.
it seems like.
There is another Ramon. You always have 2 Ramons at
Yeah.
least, right? Yeah,
Take the other one, that particular Z integral, you do this 4 times.
exactly. So that integral otherwise will not be periodic, right? So one is that you try to make this double on along the one along from 0 to 2 and 0 to 2 tau. Then it's a periodic integral, right? And you are done with it. Or you do over the parallelogram 0 to 1, 0 to tau, right? And then add the contribution from the other 3 other spin structures.
But if I fix the position of the Ramond, I am saving myself from doing integral.
No, one Ramon you have to integrate, right?
Yeah, one, but if I fix NS, I am like computationally, I am at a loss, right? I have to do 2 integrals over bigger domain.
No. Only one integral you have to do over bigger domain.
If I don't
Fix Ramon, fix NS, right? Integrate the first Ramon over the double the cycle, right? That will automatically sum over spin structure. You don't have to do the second one. Once you do the first Ramon, right? This, then the second one you don't have to do.
Oh, okay. And if I have say 2n Ramond insertions, then I have to do over this double the domain, 4 times the domain for only the n by n.
No, only one. Only one.
Just one.
Yes. Because you see, the point is, once one Ramon sector has gone around this, right? You change from NS to the periodic to anti-periodic and vice versa, right? Similarly, once it has gone around this cycle, you change to periodic and anti-periodic and vice versa, right? After that, other Ramon sector vertex of water, there is no need to do anything, right?
This integrate is the torus correlator, right?
Torus correlator, yes. Of a fixed spin structure.
Yeah, of M.
N, yes.
N sector states and N R sector states.
And all those chi's and everything, right?
That-
Yeah.
I should rewrite it as a sphere thing, firstly, to compute.
No, you don't have to. Yeah, to compute it, you can write that as sphere thing. Yeah.
So
Hmm.
I'll reduce the phi R phi R C.
Hmm.
There you're saying I will not sum over NSR and 1 plus. P.
There you have no, don't do anyway. You fix it.
Because I'm doing- No.
Even there you fix a specific sector, right? Because once you said that you have to sum over spin structure, right? Then on sphere it doesn't matter. You fix a specific sector.
All this spin structure sum was regarding that only, right? When
True.
you relate the torus to the
Yeah,
sphere.
but once you are saying that you are ultimately summing over spin structure, you can take each spin structure, right, and reinterpret it as a term on the sphere. As a term on the sphere, from the sphere, coming from the sphere, right?
Yeah.
So each of those, right, don't have the projection, right, or NS and R sector sum.
Yeah, it's either R or it's either NS.
Exactly, either N or NS or R, or and in the other cycle you have either introduced one or you have introduced,
Yeah, exactly.
right? So each spin structure is that, right?
If I didn't do this extension of the parallelogram, I would have done that, right? To write the torus correlation function, I would have written 4 different sphere correlation functions.
Yes,
which
okay.
is sum over R in
Yeah.
the- Yes, effectively.
Exactly. Yeah.
Saying that I can compensate by doing what exactly?
By doing this, that you calculate in one sector.
That phi R, and this, I mean, I still have to declare. No?
Doesn't matter, you declare, you take NS and put a P. Projection operator, P, not projection operator, that's inside a P. One, instead of 1 plus P, you have to pick one, right? Pick either 1 or P. Okay, you'll pick one. So you put K1, NS, right? You have got a spin structure. So that gives you this correlation function, right?
Then the option, there's sum over R, I'll only use sum over NS sector.
Yes, there will some.
Exception.
Yes, so you cut somewhere, no?
Yeah.
Okay, you sum over only NS sector in this. Okay? And at the same time, you sum over, you put a P, or you said you will introduce 1 or P. 1, okay. So in this channel, you introduce 1, in this you pick NS sector, right? You can calculate this correlation function.
And if I have something on the screen.
Exactly. Now I'm saying that if you want to get the other sectors, right, you have to take this, go around this, or you go around this, right, or go around this and this. Those are the 3 other sectors.
Changing what I do the
Exactly.
do something with the external state.
Exactly. That as you move the external state around, right, it automatically takes it from NS sector, Raman sector, and the P to 1.
Suppose I was only working with NS sector insertions. There was no R sector.
Then there's a modular invariance. You remember that. In the end, if you are working in only NS sector, you can't get a modular invariant partition function.
No, in the external state.
Oh, in the external, yeah. If in the external state you have only NS sector, right? Then you cannot do this. Then you have to pass some over also. Yeah.
By hand.
Exactly. Yeah. Right. Well, you can do something, but that's I mean, not very useful perhaps. That you can say, okay, I'll introduce 2 more Raman sector states, right? Okay. In the OP, there's identity operator. That's the one I am interested in. Right? Now take one of them, go around and come back here, right? And then use the OP to pick up the identity. Okay, you can do this, but yeah, I mean, let's not worry about this, right? I'm saying that this is I was trying to explain why I think of the sum over spin structure as part of integration over MGMN. Okay? That if we do have a Raman sector states, then you can actually do the perform the sum over spin structure simply by extending the range of integration over one vertex operator on the double of the torus. Yeah, the same argument will work for higher genus also.
But in that you can do G of them.
Yeah, you have to do this, take this and go around each cycle. Right? There are 2G cycles, right? You have to take the Raman sector vertex operator and go around each cycle to change the boundary condition. See, as you go around one cycle, the one that is transverse to it, right? The boundary condition of that gets changed. No, then nothing. Then you have sum over spin structure. No, you have to sum over spin structure. So this is an alternative to summing over spin structure. That's what I was trying to say. Right?
You have to explicitly do.
Yeah. So if you want a uniform description, you say, okay, always sum over spin structure. Right?
Otherwise, if you have one R sector of R operator, then you can take that position and.
Exactly. Then you take the position and integrate over the double the torus. Okay. So this formula you have to justify, right? Why this formula, which we'll do. Okay. But before doing that, we'll try to give a slightly different perspective on this formula. Right? The same formula, but a slightly different perspective. Okay, which will be useful. Which will be useful not only for proving this, but also for proving things later, proving other things. To introduce a space PGMN, this we think of as a fiber bundle with base MGMN and fiber the locations of PCOs. PCO means picture changing operator. So this is MGMN and this is Y alphas. Okay.
Then simply like the fiber is simply then the alpha or whatever, the 2G minus 2 plus n plus n.
Exactly.
Copies of.
Yeah, so this is 6G minus 6 plus M plus N by 2. Sorry, M plus N. This is the dimension. And fiber has dimension 2G minus 2 plus M plus N by 2, right? If you count real dimension times 2. Right? This is a real dimension. And topologically, as you said, it's just these many copies of the Riemann surface itself. Right? Because the fiber that Y alpha, each Y alpha can be anywhere on the Riemann surface.
Where the base space is a manifold. What is the fiber?
The vector space of tangent vectors, right? Here it's not that. Here the fiber is also compact, right? Because the Riemann surface is compact, so the Y alphas can only take value on the compact surface.
There is like overall twist of
It's simply a product. At this stage, you can think of simply a product. Later on, we'll try to have to improve it because we don't want PCOs to collide, right? We want to avoid all these what are called spurious singularities, right? So then the fiber structure will become a little more complicated. So we'll call the T as the coordinates on the fiber.
plus 2 n plus.
Yes, thank you. Because you're counting real dimension. So T we define as the coordinates on the fiber. Right? It could be taken to be U and the Y alphas. Right? A simple way to label the coordinates, right? The coordinate of the base and then each fiber is labeled by the Y alphas. But it can be more general. Right? For example, you could take this as one of the coordinate directions. Right? Because PGMN is the total space of these many dimensions, right? This plus this. And in that PGMN, I can introduce any coordinate system that I like. Right? I don't have to keep this decomposition into fiber and the base separate. Okay, but if you want, you can do that.
I was meaning total space, I guess, not on just on the.
Not on the fiber, on total space, on PGMN. Thank you. Is this clear? Okay. And in this language, PCO choice corresponds to a section SGMN of PGMN. So this is a section. That the choice of the y alphas, right? Because those are completely arbitrary, right? Okay, each PCO location can move around. Yeah, you can put them anywhere. That choice can be thought of as a choice of a section. Because given any point on the moduli space, it tells us what PCO locations you have chosen. Right? Go to a neighboring point, you have another set of PCO locations. Is this clear?
Y as a function of moduli.
Exactly. PCO choices y alpha as functions of moduli. And I'm saying that you can think of abstractly as the choice of a section of this fiber bundle.
So then it was independent, it just be a flat.
Yeah, if it was independent, it will be just a flat. Right? But that statement itself will depend on exactly the coordinate system, because if it was flat in one coordinate system, right, as we discussed, that if you go from the disk to the next sphere, it may stop being flat, right? So being flat is not a very unambiguous statement, right? It's not an invariant statement. You could change coordinates to make a flat looking object non-flat. Is
The choice of section will not matter in the end, right? Because of these factors, right? The Jacobian kind of thing.
should not matter. We have not proven it, right? We'll prove it that choice of section doesn't matter, right? Because that's why that better be the case, right? Because if the things depends on the choice of the PCO locations, then you have extra data, right? We don't want scattering amplitude to depend on extra data.
Del y, if I choose y, so that del y by del equals 0.
But that is y in a particular coordinate system, right? That if you have chosen a y in the W coordinate system, that, as I said, this statement is not continuous, because suppose you change continuously to go from the W to the Z,
What is the
The-
different spheres?
different sphere, this versus sphere, right? We discussed that.
Independent of modulus is particular, but from the disk to the sphere.
Yeah, exactly, right? That suppose it's constant on the disk, right? Y location. If we just move it across the boundary, it will no longer be constant on the anymore, right? In the new coordinate system. Okay? And that will be compensated by this residue of Bi, as we discussed. Okay, so that's the sense in which the Y, this being flat, of course, you can take part of the section to be flat, right? But that's a coordinate dependent statement. I'll keep this. So what you are going to do, that we regard okay, so whichever formula we had, we just replace Ui's by Ti's, right? So let me explain this. So omega G M N P function of the V1 to Vm W1 to Wn. Okay, so now let me write, these are the Ns and these are the Ramon. I'll write this as integral where bi's will be given by the, oh, and then let me write this in more. Okay, so let me write this as B I1 to B IP, DT I1 to DT IP, and BIs will be given by a similar formula. Okay, I'm using the same index I, but this index I has more entries, right? Because this I is the U, right? I had used the index I for U, right? That was only this many dimensional. Okay, now the I that I'm using for T has this plus this, right? Because all the fiber coordinates are also part of the of the space, right? Bigger space, PGMN. Pardon? Yeah, because this is base, right? And this is fiber. So the total is fiber plus base. T is the coordinate on the fiber bundle, right? So whatever was the base coordinate is there. On top of that, there's a fiber coordinate.
Total dimension of P is this plus that.
Yes. Total dimension of P is this plus that.
But then we are introducing some redundancy in the description of what. Because
Yes, we are introducing redundancy, but ultimately, this the result is over a section. Integration is over a section, right?
but this formula has a redundancy right now. Yeah.
Well, no, it depends on what you mean by redundancy.
It's now really greater than 6g minus 6.
Yes, it's you have to add those many numbers, right? But it's a P form in that space, bigger space. Yeah, right now it's just a P form, right? So the P now can go all the way up to this. Earlier, P could at most go up to this. Now P can go up to this, right? So in that sense, there's a it's a bigger. You are allowed more things. I did. Oh, nothing. I mean, I have to say M and N, right? I could have used V1 to Vm plus N, right? But I just uses different symbols. Okay, so let's first check that this makes sense, right? What I've written here. Okay. So here Fs was a function of sigmas and the moduli parameters, right? Now I'm saying think of the moduli parameters as a function of T, right? What does that mean? That given T is, once you fix T, right? You fix a point here, somewhere in the fiber bundle, right? Okay. For that T, there is a U, right? Because you can go to the base. right? And there is a fiber. You can go here, y alpha, right? So when I say del del Ti of this, right? The Ti dependence comes through u, right? Because u is a function of t, right? And that's what this is supposed to do. Similarly here, and here, similarly y beta is a fiber coordinate, but a fiber coordinate is also a function of t, right? Once you have fixed t, both the base and the fiber coordinates are fixed. So in that sense, u is a function of t as well as y is a function of t. Okay, and this is what it means.
Where did the section come?
Section hasn't come yet. I'm introducing this in the bigger space, right?
In the full fiber.
In the full fiber bundle.
What did y and u should be thought of as functions of t?
Yes, because once you function means what? That once you have fixed t, you should have a given value of y and given value of u, right? So when I say u is a function of t, that's what it means. That I have fixed a point t, it should have a definite value of u. And it does, right? You take any point and forget about the section. Okay, if that is confusing you, you just remove the section. The section will come later. Given any point, right? How do you find u as a function of t? You just draw a vertical, right? See what point in the moduli space on the base it corresponds to. Similarly, given any point t, you can find out what point in the fiber it corresponds.
Like say x is a function of x comma y.
Point is a function.
True, yeah. Yeah.
If this was not a trivial calculation,
If it is not a trivial,
trivial calculation, just base times some fiber.
no, so here you are doing local, right?
Yeah, so,
Ultimately, whether it's a trivial fibration or not, you don't know.
but this statement you know that fixing t.
The section may not be trivial, right? Locally, it's a product. The section that we'll choose may not be trivial.
Maybe let me understand. You have a base.
Hmm.
You have fibers.
Yes,
These y alphas are the fibers.
exactly.
So now what do you want to say? What is t exactly? T is some point in this full fiber bundle.
Exactly. T is a coordinate system in this whole fiber bundle, right?
You basically trace the fiber back to the base.
Yes. Giving T means you fix a point on the fiber bundle.
You trace the fiber also. Just think you just take that u
Exactly.
and y alpha.
Y alpha is already fixed because it's some fiber, some fiber.
Yeah. So once you have fixed T, right, you can go to the fiber or you can go to the base, right? So both y alpha is a function of T and u is a function of T. Just look at this diagram, right? If you have given,
The problem is because
no, y alphas are points. No. Y alphas are, this is arbitrary choice of sections we are talking about, right? Y alphas level all possible choice. That's the meaning of fiber, right? A section is a particular choice, right? But when I say that the fibers are leveled by y alpha, yeah, you let them arbitrary choice, right? Arbitrary y alpha. So y alphas take value on the Riemann surface, right? Each y alpha is a point on the Riemann surface. Yeah, you think of them independent, but once T is fixed, then that corresponds to a given point in on the Riemann surface, right? Given set of points on the Riemann surface. Because T knows about everything, right? It knows about the base coordinate and the fiber coordinate. Is this clear?
Ashok, can you hear me?
Yeah.
Now the top form is not modular space, like it's
No,
not
the
equal.
top form is not. Top form is much bigger.
Yeah, so we need to integrate over some 6z minus 6 plus m plus n dimensional.
You are not going to integrate over that because you are going to integrate over a section
Oh yeah. Okay.
whose dimension is the modular space dimension.
Yeah,
right?
yeah.
So now we draw the section back. We choose a section, right? This choice of section corresponds to how we have chosen the PCOs. And now the claim is that the amplitude I forgot minus 1 over 2 pi I, that factor. It's always there. The amplitude is, yeah.
This thing may have a problem when two y alpha. You said something more.
Yes, so we'll deal with that later, right? Right now we are not we are ignoring that issue, right? But later on we'll see how to deal with that, right? We don't want the two y alphas to collide, right? That's why the fiber is somewhat non-trivial, right? It's not just product of Riemann surfaces. Okay, so amplitude is given by integral of omega gmn 6g minus 6 plus 2m plus 2n over a section. So omega is a form in bigger space, right? PGMN. But when you say you are integrating a form in PGMN over a section, that basically means that you are integrating the pullback of that form on that section. Right? So this is a pullback on SGMN. Okay, and it basically is the same formula that you had earlier. We're just reinterpreting this in this way.
Could have been degenerate or
Could have been?
degenerate.
What could have been degenerate?
The form itself has no, depending on what section you do,
Hmm.
it has no corresponding visible. I mean, these T1, which T2 corresponding to that.
Well, that question you could have asked even earlier, no? No, but this is the same formula. It's not a new formula. It's just a rewriting of the original formula, because you choosing section means what? That you are choosing T as a function of the base, right? Base coordinate, right?
There are 4 dimensions,
Yes,
and you wanted two form.
yes,
And it's like trying to define that two form on some surface.
Yes.
2-dimensional surface in that 4-dimensional.
yeah, exactly.
But that,
So there's a well-defined notion of pullback, right?
but a specific two form may not have a well.
No, every two form has a well-defined pullback on the surface.
It's just some, let's say XYZW,
Hmm.
R4 or something.
It may vanish, Suppose you are put to,
degenerate means
which is okay, then the result will be 0, right? I mean, it's the same result as what you had earlier, right? Because if this choice of section, okay, this choice of section is basically telling us how y alphas change as a function of t, right? Once you think of it that way, right, this formula that I have written here is exactly the same formula, right? We're just reinterpreting it in this language. Yeah. So one of the use of this, right, is the following. Suppose you want to say that how do you show that two different choices of picture changing operators gives you the same result? Two different y alphas, which was two different sections, right? So we are now saying let's take this section and another section. Okay, we are trying to calculate the difference between the integral over these two sections, right? What we'll do is we'll show that this can be rewritten as a integral of a bigger form in this space that is in between these two. Okay, because this is an integral over a 6g minus 6 plus 2n plus 2m form, right? Now it will be a 6g minus 6 plus 2n plus 2m plus 1 form, okay, integrated over this region. Okay, that
is what difference of these.
yes, because take okay, let me say what the new form is just d of this, d of the p form, right? If you try want to calculate the difference between SGMN and S prime GMN, right? Take d omega and integrate over this region, right? Pardon? Stokes law, yeah, exactly. This is Stokes law, right? Nothing more. So d omega integrated over in this range, right? Okay. What will show is that d omega is 0 for physical external states. It's not 0 identically, right? But as long as the external states are BRST invariant, we will show that d omega is 0.
mean, apart from few things, it can be, it's mostly non-degenerate also. I mean, in some cases can be degenerate with using zero.
Yeah.
Then it's giving a definition of symplectic form also, right? So basically,
You're giving a different
I
symplectic
mean,
form.
this form looks like.
No. See, we have a difference between these two omegas, right? I'm saying Stokes dot elsewhere is d omega integrated over that region. That is clear, right? This is.
Section.
But why is d omega 0?
There's no dependent section for the other way.
No, but that's what you are trying to prove, no? That it doesn't depend on a section. So,
That's what we are demanding.
no. We are demanding many ways. That was written by so that it happens, right? But now we'll show that d omega, right, for external BRST invariant states actually vanishes. Okay? And you can see that this kind of argument you couldn't do, right, by remaining in the moduli space, because d omega there is identically 0, right? Omega is already top form. So d omega will be 0 identically, right? It's only by extending this thing to a fiber space, right? We can reinterpret this as a bigger form, right? Higher form. And then you have to show that that higher form actually vanishes.
Differential form defined on all sorts of bases.
Locally, yes, right? Sometimes it has singularity, if that's what you mean.
Firstly, even the moduli space is not a good manifold. It has some.
Yes,
kind of whole structure.
exactly.
Manifold.
So you have to deal with those, right? The singular parts.
Yeah, that's singular,
Hmm.
just within MGM.
Exactly,
And then there will be more perhaps singularities because of evolution.
exactly, yeah. So all of that you have to deal with.
So, it takes Stokes theorem, but it's
Yeah.
not very obvious.
Yeah, it's not obvious. It's obvious except as those singular points, right? So the singular points you have to deal with separately. Yeah, so the singular points you have to deal with separately, right? Which you will do, right? We identify what the singular points are, right? Singular points are basically boundaries of the moduli space, right? So you have to make sure that from the boundary of the moduli space there are no problems. And the points where the things collide, picture changing operators collide.
Because moduli space or Riemann have some special properties that Stokes theorems and all.
No, it will not happen unless it's a string amplitude. I mean, you can certainly write down forms for it, this will not happen, right?
I think these are specific forms. also.
Yeah, so these are very specific forms that come from the string amplitudes. These have the nice properties, right, which makes things happen because you have the physical picture of what kind of.
Yeah, general ghost form on MGMN,
Hmm.
those locally. If I just try to do a Stokes theorem,
You will get a boundary term from them. Exactly.
Because
Yeah.
of this orbit, or not orbit, I don't know.
Extra
They are singular point, boundary. Yeah. Right. But in string theory, those singular points are very specific meaning, right? They are basically massless, they are light strings propagating in the along propagators.
But you see somehow in these specific cases, apart from these two boundaries, I mean, these two sections,
Hmm.
other boundaries which are inside it, they somehow cancel each other. I mean,
Other boundaries are basically the boundaries of the moduli space itself, right? And the points where the picture changing operators may collide.
Just one. If you are doing not heterotic but nice, you will just add the conjugate part.
Yes, yeah. There will be y bar alphas and you have to include those also.
now we have to prove that d omega is zero. D omega-
Yes. So you'll write down some relations involving d omega. You know that we'll basically do two things at one go, right? One relation that will prove some expression for d omega in general, right? And then we'll show that first of all implies this, that the picture changing operator, the location of the picture changing operator doesn't matter. And it will also show that if we have a one vertex operator is BRST trivial, right? Others are BRST invariant, then the answer automatically vanishes. So that will be a general relation that relates d omega p with omega p minus 1. Sorry, omega p plus 1. Because d omega p will be a higher p plus 1 form, right? That will be related to omega p plus 1.
I think if you're done, and then I have some tangential questions.
Okay, yeah, sure. Yeah.
Because this, I mean, okay, this fiber bundle is even dimensional because we can see that at least in real dimension is even.
Yes. Okay. Yeah.
Even, and then it has a form also on it which is also, I mean, which is closed. D omega is closed.
D omega is closed only.
Sorry, omega is.
Omega is okay. Omega will be closed. Only when the external states are physical. Omega is not a closed form in general.
So, let's say I am only considering that case, external states.
Okay. Yeah.
Then omega is closed, and perhaps in some specific cases, omega might be degenerate also, but non-degenerate. It does
Okay.
not give zero value, right?
Yeah.
Then it looks like this fiber bundle is have a natural symplectic form on it. I mean, basically, it's a symplectic manifold. I mean, because it has all the properties.
Symplectic form is a two form.
I mean, I feel if I restrict that such that it is two form.
Yeah. It could be. I don't know. I'm not sure if it. Yeah.
That's a very specific case.
Hmm.
Yeah, it's not. Yeah, to start, it's not a manifold.
Hmm.
I don't know whether there are symplectic structures or non-manifold.
But I mean, suppose you do have a symplectic
Yeah,
structure.
define something like Hamiltonian flow and all these things.
Yeah, you may be able to do. Yeah, I mean, whether one can make use of them is a question, right? Yeah, it may be useful also for some things.
But I don't know what them physically is. Okay, but
Okay.
What does this surface space of?
No, on this fiber bundle, there are many things can be do. You can write a BB master equation on the fiber bundle, right? Without referring to anything else.
The full dimension of this some number, that 6G minus 6, that has any Riemann-Roch like meaning? Or
The full number, I am not sure. See, individually, of course, they do have,
yeah,
right? Because, but full number, I am not sure if it has a Riemann-Roch kind of meaning. But the base has a Riemann-Roch meaning, right? It's the dimension of the moduli space, and the fiber is basically how many PCOs you need. That also you can get from.
Probably then the supermoduli dimension of that, or
Oh yeah. Two supermodular dimension is the total, right? Yeah, exactly. But the point is that there are some Grassmann odd and some Grassmann even dimensions, right?
have to make that.
Yeah.